Today, we're talking about a massive leap forward in computing history. Harvard researchers have just cracked the code that has stumped physics for 30 years, potentially bringing us decades closer to a true quantum revolution. Harvard researchers have built a quantum computer system that actually gets more accurate as you make it bigger. Previously, making them bigger made them crash faster. They used lasers to trap 448 atoms and corrected errors in real time, which is the holy grail for making these computers useful. Historically, the problem with quantum computers is the errors, because you never can tell whether you actually got a correct result or it's just another error that happened to error out on this correction. But they're getting closer and closer, and there's lots of technologies that seem to be handling this in different ways. But this sounds like it really has taken that a step further.
Yeah.
What's going on here, John?
Yeah, I think this is another one of those breakthroughs that's going to help us bring up that timeline for quantum computing, practical quantum. So Harvard system, what they did was it employs surface codes, which is a leading quantum error correcting code that arranges physical qubits in a 2D grid structure using up to 288 atoms arranged in code blocks. So the team used optical tweezers to trap and control arrays of rubidium atoms, with each atom serving as either data or ancillary qubits that are moved and entangled using precisely calibrated laser pulses. The surface code operates through repeated stabilizer measurements, which are a combination of qubits that reveal whether an error has occurred without actually measuring the quantum state directly. So that, which obviously would destroy the quantum information. So each round of error correction, it involves measuring stabilizers followed by classical decoding using machine learning-based algorithms, which are optimized to handle atom loss, which is a common problem in neutral atom setups. So the way the system works is it leverages what they're calling quote-unquote superchecks, which are products of multiple stabilizers that remain valid even when individual stabilizers fail due to atom loss, which provides redundant error detection. And based on what I've read and based on this thing, this breakthrough could mean we see practical quantum computers in the next 5 to 10 years. What do you think about this? Do you think this is the breakthrough that we've been waiting for, Craig, with error correction, or is this just another potential?
This is another potential. I mean, I think we've seen a lot of technologies where, some of the chips are building, they build, say, a 7 qubit chip where 4 qubits are for error correction and 3 are for processing or something like that. So as we get to better and better processing, and the more you add, the less errors we have, that is going to scale much better than our current situation, where the more you scale, the more errors we have and where things break. And if we can actually get to long-running systems, because that's the problem, is they can only run for, minutes at a time right now before they start to, lack of a better word, blue screen of death, lack of a better relatable metaphor. But if this error correction will allow them to do hours, that's, fantastic.
Yeah.
And, taking these things to the next level. Yeah, I agree. Building a machine with millions of qubits needed for the big stuff is likely 10 plus years away. So we're going to be, from that point of view, but we'd like to see the error correction in 5 years or so we can start building moderately qubit machines to do this kind of stuff.
Yeah. So let's put this into perspective, right? I'll just try to put it into different perspective. So imagine trying to perform surgery while riding a roller coaster during an earthquake. And that's essentially what quantum computers have been trying to do: perform incredibly delicate calculations while being bombarded by noise from the environment. And so this breakthrough, it could represent the first time researchers have successfully built quantum, let's call it noise canceling headphones that get better as you scale up the system, to put it into perspective, right? I know we actually covered, I think, another quantum error correction that got better with the larger amount, but this is different. This is a different approach to it.
Yeah, and fault-tolerant quantum computing opens doors to applications previously considered impossible. Molecular simulation for new pharmaceutical compounds, protein folding prediction for disease treatment, personalized medicine based on quantum analyzed genetic data, breaking current encryption methods, developing quantum resistant security protocols, and secure quantum communication networks. Also in artificial intelligence, quantum machine learning algorithms, optimization problems in AI training, and pattern recognition in massive data sets. In finance and economics, it's risk analysis and portfolio optimization, real-time fraud detection systems, high-frequency trading algorithms. In material science, the design of new materials with specific properties, catalyst development for clean energy, and semiconductor research. Like, it will change like everything.
Yeah.
So I'm excited to see where this is going and this breakthrough. Let's hope it gets out of the lab and the quantum computing companies start using this and it works.
Yeah, for sure.
So we have finally crossed the threshold where bigger actually means better in the quantum world. Does this make you more optimistic about seeing quantum breakthroughs in your lifetime? Let me know your thoughts in the comments below. What do you got going on, John?
Yeah, just gearing up. Is this coming out in December?
Yeah, December might even be January now, actually.
Okay, gearing up for the holidays or gearing down from the holidays. So planning out my next few months and, ramping up for shred season. How about you, Craig?
Well, we're wrapping up 2025 and planning 2026. So this is probably too late for the start of investor drinks and Flowgrammer events in December, but take a look for them in January. There's always stuff going on. Check out torontostarts.com for our startup and business related events and resources, and check out flowgrammer.ca for our business and AI automation information if you're looking for that. And if you're a builder in Toronto and you want to join the Flowgrammer Builders Club, head over to flowgrammers.ca. That website is live now. Go check it out. Join us at our live events. We do online stuff. We do live office hours every week. Go over there and sign up. There's downloaded workflows and tools you can test and play with. So check all that stuff out. But John, if people are looking for non-dilutive funding, where do they go?
Yeah, come find me on LinkedIn. I've got a link. You can book some time with me or send me a message so that we can have a conversation first. But find me on LinkedIn, John Irwin, no H. But if you need help with your business overall with your startup, how do they get in touch with you, Craig?
Head over to startupcoach.ca or torontostarts.com and just book a call with me and get a discovery call, find out what's going on and get you motivated. If you're not interested in that, come out to one of our events, talk to other founders and whatnot, and just talk to people. It really is, knowing that you're not alone can motivate you a lot. But other than that, give us a call or book a meeting over at torontostarts.com. And thanks everyone for listening or watching, and hope to talk to you again soon.